All right, ladies and gentlemen, take your seats and bring me your questions, or at least bring them up forward. We have some, excuse me? Yes, we are photometry. What is photometry? That's in the next room over. All right, so I'm going to walk out of focus here for a second and put this down so I can walk by it and hand it out, or let somebody else work with handing it out. We had some long conversations yesterday based on part and parcel of the workshop, and then based on the fact that we haven't seen each other for 3 years. It's good to be back, and it's good to see everybody. Hope everybody's doing well, both at home and here. Really what we're kind of coming down to is when you ask what is photometry, I've been saying something for the last while, and that is don't pay attention to the signal, pay attention to the noise, because you can do something about the noise. And then if your wallet is big enough, you can do something about the signal. You can acquire some additional acreage of aperture. In general, metery means that you're taking something and producing an objective result. Something along the lines of just an observation is where you make a visual guess at a ratio between, say, two light fields based on some two chart numbers on a star. And you can get very good at it. And there's volumes of that information that's been around for centuries. But the minute that we were able to make a record that was objective, and that was, I made a photographic exposure or something along those lines, I could put that in an envelope and mail it to you. Remember the mail system we used to have? The mail system would take it to you, and then you, by your own independent means, could interpret that data to your purposes. That got subjective there, didn't it? So in large part, we set up our equipment and we set up our observing programs based on the relationship between the signal that we need and the noises that we have to survive. And so I think that's probably at least a good opening definition of what is photometry. And then beyond that, there are a lot of instrumental systematics that you need to learn for yourselves, and you need to spend some homework exercises. Moon nights are good, full moon nights are good to get out and practice with your equipment. And what you're going to find out is that you're going to have to make adjustments in some ways in canned software, in some ways a lot of these guys here have been telling me they roll their own, to deal with the filter to filter variations. Am I using vendor A's filter versus vendor B's filter? How does my QE curve for my sensor stack up to the QE curve for your sensor? We find out we have the same sensor number, they were bought at different years, are going to be slightly different. So those are the kinds of things that in the best of all possible worlds, we want to have two numbers from the same source that would agree down to within the noise that we can have. If you're looking to see that something's just wiggling, differential is just fine. And I can tell you from the differences in those magnitudes that indeed I'm at some phase or some relationship. I don't really need to know the flux from it. I don't need to count those photons quite as accurately as you might think. When it comes to counting photons, we're all over the map as well. I live at about 5,000 feet. I think Tony Rara, there he is. You live at what, about 60 feet? 62 meters, okay, woo. You know, you wear oxygen up there. Okay, so he says he does. So we have members, I think Tom Smith's probably with us in the background there somewhere. He's up at about 70-something hundred feet. A friend of mine lives at 10,500 feet. And so the higher up in the air that you go, the less impact that you have with what we might think of as changing aerosols. So one of the people I was kind of hoping to get here this year was someone who would talk about the air that we look through. And I think that's probably a good topic for a workshop maybe next year. Is get Steve Albers or someone like that to come in and really give us an absolute mind-numbing detail, all of the aspects of the air that we're trying to look through. You can do science in the city. That's another big message. So when it comes down to photometry, you don't have to be outside. You can be in your backyard, literally. And yes, you're going to have a little bit noisier data, but you know, good, good, okay data is a lot better than no data any time of the week. All right, got one on the ground. Everybody should be quiet. So we're going to start off with a question here from Mike Hoffert. The QHY 600 and an awful lot of the cameras that we use don't have shutters. How do I do darks at night with their lights turned off? So that's one good answer. The other thing is you can put a shutter mechanism on there. You can put a slide mechanism in there. There's just a number of different ways that you have to dream up for yourself in order to keep the ambient light off of your chip. Okay.
Have John who print you a blank filter for your filter wheel, right, John? Did you bring it with you? And then paint it black so it's IR transparent, not transparent.
Yeah, in the spectrography world, we found that gray ripping black PLA was just about a window into IR. And by the way, we've done a lot of experiments with paint. So while we're on that subject for just a second, run-of-the-mill flat back black paint is anything but flat black. If you the best paint I found in the shake and shoot world is the Rust-Oleum Camo flat black. It has 2-micron particles embedded in the base. There's a fellow out in California who runs Astrosystems. His name's Randy Cunningham. He's a chemist by trade, and he took every flat black paint he could buy anywhere in driving distance, and the Walmart Rust-Oleum Camo flat black was good. Clark Yeager here, did you bring that coupon with you? Okay, later we're going to be demoing our spectrograph. We will bring down this little coupon, as we call them, where I think you took your best guess at flat black. Then we spray painted camo on top of that. It was like, whoa, this is different. And then Clark did a lot of investigation, and he found this stuff that you can buy on the internet called black ELK3, right? Do you remember the name of the company? Google it, you'll find it. That stuff is remarkably black. ELK3, okay? It'll come up, right? Google's wonderful, it finds all kinds of stuff that I never knew existed for my credit card, which my wife wished I never knew existed. So something else that Tony Rada has done is he uses this aluminized tape that you buy for putting heating ducts. That is opaque. It's stickier than heck, but it is opaque. And so that way you can caulk up some of the light cracks. I got a spectrograph from Jeff Hopkins way back many times ago, and he had taken black electrical tape and sealed his unit up. So when I say you have to be inventive and creative about getting rid of light leaks and things along those, leaks are a good one because there's a hole drill somewhere, like in the back of a filter wheel, or something didn't quite made in there. Then you're in there. Or you can print this, I won't say it, lid-like assembly that we have that we can push a button and a little microprocessor will open it, a little button will push it closed. And that way it allows us to add a shutter mechanism to a lot of the existing spectrographs. And the way we do this, we stick it in the nose piece. So if you have a camera mechanism coming out through the back, you can put one of our little shutter mechanisms right up in there. You probably want, well, you may or may not want the cowls and flats on that. Okay. Other exposures, you don't have to worry about too much. I think I wanted to do my zeros in the dark with that camera, but for the most part, it has its own shutter mechanism. And when you initiate the shutter mechanism, it drains the pixel down and takes a snapshot of that low pixel level. Then it allows the signal to build up through the quote open shutter exposure time. And when you stop it, it quits accepting photoelectrons, gives the difference and reports that back out. So in that regard, the shutter's not needed. See what I mean? And then the other thing, if I'm a camera manufacturer, why do I want to put a shutter on everything? It's like you go to the store and you buy some USB gizmo, and they send you three USB cables, and you've got, you just add those to your war chest with USB cables at that point. Lately, it's to the point now, if you buy something, you have to make sure to buy the cable in addition to that. All right, so I'm going to leave that one. Did I get your question answered well enough, Mike? Okay. Follow up.
Maybe one other thing to mention though is that the blank filter is potentially still not enough because you have other filters in that wheel. Light comes through those and around. And so
Exactly.
you really have to, throw the dark sheet over the aperture or whatever.
My strategy on that is if I have narrow band filters in my filter, I always sandwich my blank between narrow band filters. Really, you should, one of the tests you should do, okay, is actually whether the light's on and you don't. Take what I do, make sure that I not shooting the feet off, is that I take a dark with the roof on my observatory closed in the dark at night, and then I turn on the lights in the observatory and I take another dark. And if I see anything significant, that means the train has a light leak, and then the fun begins. Find it, fix it.
Okay, I'm going to make a note here real quick. That's one of the most duh-ist answers I've gotten here. Turn the light on and make sure you're not leaking. Like what becomes of these things?
Hey, Wayne, people online are asking people to speak clearly and to keep the microphone when they're talking, so that's taking care of.
Okay, so okay, that was you doing that. Okay, things beep at me too. So for some people, don't hold the microphone down like this. Speak trying to directly at it or into it, like Gary's doing that nobody can see. Yes, Gary.
Yeah, one tip on using the, sorry about that. One tip on using the aluminum tape. If you use the blue painter's tape, you put that on your equipment first, then you put the aluminum on. When it comes time to take the aluminum tape off, you don't have to use an X-Acto knife blade, and your equipment is still in decent shape.
That's very true. There's one other caveat that I want to mention. Move mine closer. Okay. So one of the one of the things I was going to mention with tapes and everything is they are adhesives and they will outgas. So be very careful about letting material evaporate, particularly you guys who live in hot climates, like me in the summertime. Okay, Mark.
There was a comment made that PLA doesn't block light out very well, and that G with carbon, I ran a little experiment with that. I took an exposure in the house, covered up and everything, and I set it outside with a cap on it. That G pointed right at the sun and saw no evidence of light.
Right. Okay, so the PETG is a plastic material for 3D printing, and it has embedded in it small carbon fibers. It's PET is the compound. PET with carbon is the rest of it. So PETG. There's a whole host of these things. So let's see what might next be. Go to. Okay. That's good. Thank you. Yeah, you were turning the knob. I saw you. So discuss processes for mitigating telegraph noise. I'm going to postpone that one for just a moment or two. I think that would be a good can of worm opener. Here's a good one. What is the best way in crowded field in a roll your own software environment to get a good, consistent measurement of background sky noise? Jerry Foote, There's a microphone. Bob's got one for you.
Hello,
Yes.
take Arn Hendon's advice, choose a different feed. Thank you.
I might add that focal length helps there to a degree. Okay. I'd actually discussed that with a question talker before, and I tend to use Sextractor, and you have to be careful with it. You have to characterize it. You have to be pretty consistent in its application, and it's like a little dog. Uh-oh. I just dropped out. Did my battery die? Okay. I'll see. I'll just keep rambling around here for a minute. Okay. Well, then that basically. So people at home, I really hope we're getting the sound better for you. Okay. So somebody. Okay. Excellent. We found the happy medium. Okay. Where were we? Crowded field photometry. Peter Stetson, I think, took on that question with DAO Photo 2 and sort of kicked it in the pants there. There's a lecture on all of this that's on HTML format on iPac. It was sort of a transcript of a lecture that he gave in Brazil. I actually, don't ask me why. I typeset it. It came out to be about 90 pages as a PDF. And typeset it for myself because I kind of like, I don't walk on people's copyrights unless I have to. So what happens there is a lot of interesting assumptions that are made underneath of the techniques. For example, Pearson's estimate for getting the median value is not where they just line all the values up and pull one out of the middle. They use something like, what is it, 2 times the mean plus 3 times the mode or something like that. Or the mode is 2 times the mean times 3 times the median, something along those lines. That's on Wikipedia. John.
I'm raising my hand for a comment online. Eric Doe says, for accurate sky background, just use AstroPi's SpotUtils package, the Sigma Clips median algorithm. I talked about that in 2020 and 21 at the SAS, so look up his papers.
That's very true. Thank you, Eric. You've reminded me of that a number of times. How many people have access to AstroPi? That's a big question. We'll get to that in a moment too. John, can we make a note to put these chats out on a text form file and put them maybe with the proceedings somehow? Or mail them to people? I don't know. Well, folks, we'll try to find some way to disseminate the chat information for you. Yes. There we go.
With regard to photometry and cluttered fields or with close neighbors, occasionally I have the need to do that and I can't take Arnie's advice. And once upon a time I used DAO Photo successfully, and that machine has since died. And I haven't been successful getting an IRAF installation on Linux since then. So does anybody happen to have a virtual box that's
right beside you?
Yeah, I have in fact, I'm running it right here, right now, processing some data. No. See me and we can make an arrangement that if you've got space on your hard drive, it occupies about whatever, 55 gigabytes, and it has all sorts of data reduction tools. But if you have a Linux package, I don't know what version of Linux you are running, but I just put 2204 on my machine, and I typed sudo apt-get install IRAF, and it's in the repository. Boom, I had IRAF.
Okay, there's a secondary way of doing that as well, and that's under the
And
AstroPi package.
DAO Photos is part of the packages that's in there.
Okay, well, I mean, there's 100 ways of doing this.
No, this is a good one.
Wait,
Google-
I want to make a statement here about IRAF. The death of IRAFs has greatly been exaggerated. It's currently under community support by Ole Steacher. You can find it on GitHub. And I checked a few weeks ago and found an update had been done within hours of my checking. So, John?
Okay, here, Google multipass, MULTIPASS space IRAF. There's a website called Scipedia run by a couple guys at ESO in Spain, where they have a detailed page that tells you how to use the virtual machine multipass to set up an Ubuntu Linux partition, not partition, but like virtual machine that will run IRAF perfectly. I had the same problem with DAO Phone. All my stuff relies on it. It works perfectly with it. You can see me later if you want more. Multipass, yep, MULTIPASS, and the IRAF. Google that, it'll come up first.
Yeah. I've had some modicum of success running it out of a Docker container, as long as it doesn't try to bring up X Windows graphics. You can get X Windows to run through a Docker container, but it is murderous. I will not recommend anyone even think about that. And has anybody here had any experience with Win10's WSL running Ubuntu and then doing something like VSX serve for the X Windows part? Okay, I just got VSX serve running and it did work. And I'm experimenting with, John's over there shaking his head. My development machine stock Linux Ubuntu running what I do, and I seldom go to Windows. Arnie, you're using a VBox, aren't you, on a Mac? Okay. Older Mac OSs were closer to Unix. I'll get to you just a second. Okay. Was closer to Unix. iOS, this is where they're trying to build one operating system for all platforms, has sort of broken some things, many things related to old IRAF. I will go into this in slightly mind-numbing detail tomorrow morning in a little presentation I'm going to be giving on IRAF. So I think about enough said for that part. Your comment?
Yeah, and just for a lot of folks, I think VMware, the virtual machines have been around for a long time, are very easy to set up on Windows 10, 11. I've got several different versions of Linux running, real easy to switch to, works really well. Just an easy solution.
Let me comment one more thing about VBoxes. A VBox is a chunk of disk. The stuff you put in there is in there. There's some stuff on the periphery that does kind of pollute your local system, but it's not much and it's really thin and you're pretty safe with it. You change your mind and you want to move to a different Linux. Then you put that in a different VBox, the same virtual box widget, which is the stuff that's glued to your operating system. You can bring up a completely safe environment on the side. Virtual boxes are used by developers who blow things up all the time in such a way that it doesn't bring down their main systems. And that means that we can get away with bloody murder over there most of the time. Okay? Bob?
Follow-up question on the cluttered field sky background problem. One of the student projects yesterday was a variable star in the middle of a nebula. And what they tried to do is make the measuring aperture snuggled up against the star, and then the sky annulus be a big donut outside the visibly obvious border of the nebula. For Eric Dose, if they had used your approach and just ignored the fact that the nebula was out there, would that work? Or do these more smoothly varying backgrounds present a whole different problem?
I'm asking Eric to unmute. We'll see if he responds.
Hi, can you hear me?
Yes.
Yes, it should work. I think I would make some artificial similar fields artificially and tested on that before I committed.
Simulating both the smooth background and whatever kind of random fluctuations, spatial dimension that it has.
And the nebula.
Yeah.
Eric, that's an excellent suggestion. And I think it's something that I just wrote down to kind of include to go with one of the questions that'll be coming up here in a moment about collaboration. If you can simulate something, if I can build a star in a noisy field and I go and I use a seeded random number generator so that every time I run it, I get the same random number, then what I can wind up doing is I can test and I can put things in, I can bring things out and see if I get the round trip right. That's tricky. I mean, how many people here have a math major like mine? You know, not many. All right. So then the real question comes back to, how do I trust the software to get the job done? And I think that's standard fields. Or it's something that I've been advocating for some time, and hopefully we'll get it done this year, is to put up worked examples. In other words, we give you the zeros, the darks, the flats, the photometric fields, and we see by whatever technique you may choose, if you can come up with the identical answer. Another exercise that we've used, I'll get to you just a sec here. Another exercise that we've used, or Bob Buckheim and I've kind of talked about doing, is something that's right outside of Arnie's expertise. We call it steady star observation. In other words, observe the same field over and over again with no variability in it to see if you get the same result. And what you're looking at is you're not paying attention to the signal anymore, you're paying attention to the noise sources. If they're small, happy day, go ahead and leave port. If not, do a refit. Okay.
So I have found that different software packages using the same apertures, the same sky annulus, come up with different photometry, which I presume is slightly different algorithms, slightly different methods. And so has anyone actually gone to all the trouble of comparing the various software packages to come up with a winner? Or maybe more importantly, a loser?
Just hand the microphone one over.
The problem is that what is the gold standard on that? And so what I tried to do is to work with the LSST folks who are doing modeling of theoretical creation of images that have been ray traced through their entire system. So they actually have, you know, stars and galaxies and everything else in there. And the idea is that then you have an accurate knowledge of how bright each of those objects are, and then pass them through whatever software package you want. And unfortunately, I haven't found the person that is willing to do that because they're all busy trying to, you know, bring up this telescope. But if somebody does have access to somebody who makes artificial star patterns, I think that would be kind of an ideal thing to play with in order to have a gold standard that then you could run and test all the different software packages and play around with different aperture sizes and everything else just to see what it actually ends up doing. Regarding crowded fields, PSF fitting is usually about the only way that you can really handle a crowded field. And the trouble is that there's always background stars, especially in, say, a globular cluster or something like that. You can use DAO Phot and you get rid of all the stars that you think you can see. And what you see is this, you know, this diffuse background sitting there, which are all the stars that weren't resolvable and didn't fit well. So they're always there. And so it's really hard to do good crowded field photometry. You can get close, but you can't get the final answer. And I think regarding the nebula that the group was doing yesterday, instead of having the sky annulus on the outside of the nebula, I think it's much better to have it close to the star, because there's nebula underneath the star or in front of the star, whatever you want to call it. And that needs to be subtracted out too. And so it's better just to go close to the star. Rather than
we call that texture.
Yeah, that's a real.
I got one online here that
You don't want to subtract black sky. You want to subtract the nebula that's over the star.
And there's another thing too. If you go and do a supernova observation that just bam, thing pops up, it's going to be gone in 6 months. Go ahead and take all your data and then come back and visit the field when that artifact is gone. And that gives you a sense of the texture that you have. And there's some caveats with that. And that is that the scene conditions matched and the plate scales and so forth matched. John?
Eric Doze again. I should just make him a co-host or something here. He points out AstroPi's Boat Utils package already has numerous
That's what I
pre-characterized
thought.
image files. Yeah, on which you can test algorithms.
Yes. And you can also make oddball apertures out of that. Like I had a problem that had a star diagonal where the diagonal light from a bright neighboring star went right across the star of interest. That's a fun one to play with.
Was the reference Photutils?
Yeah, AstroPi and Photutils.
Got it.
Who wrote that, by the way? Is anybody claiming credit for it? I mean, not Eric didn't write Photutils, but yeah.
But in the meantime,
At the tail end of this thing, I can go into some of the details about AstroPi, but right now let's kind of avoid that a little bit. STSI, okay. I want to say something for Arnie is, have you managed to actually get around Olber's paradox yet? That's essentially what we're up against.
so even without maybe perfect images to use to compare, has there been some work done comparing the different packages in the meantime? You know, there's Maxim and Myra and VPhoto and a dozen more, and we have at least one author of one of the packages here.
Right
So,
here, yes.
Pierre.
Pierre, there's a microphone behind you. Let's hand the discussion to you for a little bit and let you answer some of these questions.
The question.
The question is how to deal with crowded field photometry and backgrounds. Oh, wait. His was the comparison of all of the different packages, one against the other.
Yes, in my program, the LSV photometry, I detect, I make first astrometry, so I know the position of the stars. And if a star is in the annulus, I remove this part of the annulus when I calculating the background level. And I can do that up to three stars in the annulus.
Okay, there's a type of aperture that you'll find under DS9, and I think it was designed mostly for use by the X-ray community. It's called a pandas aperture. And what that is a round target, like you would imagine, with concentric rings in it, and you can set the various things. It's an area thing is what you're really going for. But they put a number of selectable radials that come out so that you get these little, let's just call them rectangles that go along inside of your annulus. And that way, if something falls in one of those rectangles, in other words, its statistics are significantly different from anybody else at that radius, then you can deal with it as you may. For example, I think, Pierre, you probably just ignore it and take the sky then out of the remaining parts where that star did not fall. And that's not a bad way of doing it. And I'll say something else. I use Sextractor a lot. It comes up with a flux and it comes up with a background. And I'll select the backgrounds for the whole image and just plot a surface of it and see if there's a gradient on my plate or see if my plate is fairly level. And that's a good test. And one of the things, if you're working in the moons in the sky, the portable light pollution, okay, sometimes you will get a moon gradient across your field. So that makes it, like Arnie was saying, it's moving that aperture away from your target by any significant distance, is you're begging for any number of gremlins to creep in there.
Hi, Chuck Cinnamon. Actually, I have two questions relative to photometric processing. First one is, I tend to do a lot of time series work, eclipsing binaries, for instance. And the one thing I've noticed in VPhoto, and I'm not sure if, perhaps we're going to address it in AAVSO, is when I just do a single image, I'll get an uncertainty that seems to take into account the standard error and other uncertainty. But when I do a time series, it seems like it's just, the signal to noise. Is that something that we're going to look at, from a time series perspective to give the same kind of uncertainty that you get when you do an individual image? Yeah, so if you go do just a single image, you'll get an uncertainty that's, okay, like 0.28. But then when you do the time series, all they're going to give you is 1 over the signal to noise. So it might be like, 0.01. Well, again, when you're doing the, the individual image and, you've got the annulus, on there, it's calculating the uncertainty based upon more than just the signal to noise. So it's just an oddity that I've noticed, because then when I look at my my time series, they're all just based upon 1 over signal to noise.
Gary, are you familiar with this problem or situation?
Yeah, I've noticed a different thing. I use Maxim to reduce the images, and it reports in the AVSO format an error, and that's basically the +on error. And then if you do a time series, you'll notice that there's this much, your +on error is like real small, but the time series is much bigger, and obviously that's where we call that systematics, because that's unidentified other stuff that we don't know how to deal with. And so I have noticed the opposite of what you've noticed with VFO.
Yeah. So anyways, the second comment or question is what you were talking about before with supernovas, for instance. So I've been working with the refit guys on, looking at supernovas and other galaxies right now in preparation for the snooze work. And they're using template subtraction. And I'm wondering, with the advent of that, is that something we might see, either some tutorials or some more, so that amateurs can do more of that? Because the templates are out there. The question is, are there tools that, from the images we've taken, that we can easily, do that kind of template subtraction, especially when the supernova is buried within that galaxy?
That's a good question. I know LCO has gone through galaxies and taken pre-images called pre-discovery images. And they go back with the same telescope to get the discovery image. So that means that they have a one-to-one mapping, more or less, of their so-called template at this point to the actual discovery. And that was really important. That was pre-anticipated for 1708-17, the first significant gravity wave event. When we take stuff, and Bob, Woody, myself, and a couple other people were playing around with something called an intermediate luminosity event in, I think it was M51. And that particular problem was it popped out of nowhere and we did not have the background to look at it. Now, if I were to go to some place like Hubble, for example, you think, oh boy, Hubble, I was able to see right through that spot, no problem, because I didn't have all the blurring, all the instrumentation artifacts that I was dealing with. And I found an open cluster in there. And that was actually informative of the science, because that meant, was one of these things a straggler, or ejector or something like that from that particular cluster. But you couldn't see the cluster in the images, even in pre-discovery images taken with ground-based telescopes of that aperture. So now I come back, so let's say I take something on my C14 and you're working with your C11. If I go to try to transform that image, then I would walk into a problem that we talked about yesterday. And I think John Hoop brought this up, flux conserving. So how do we know that we have actually accounted for and reapportioned all of the flux image in such a way that it's not adding error to your observation?
Yes, no, I agree. And just so you know, I believe the way the refit guys are doing is they're taking the templates off of, I think the website's called Alerts, that has all of the, the ongoing and cataloged supernovas. Actually, it's more than supernova, but they're most interested in the type 2 supernovas, and the templates are there. So they're getting the templates from there, and then they're manipulating the images that us as volunteers are sending them and rotating them and lining them up. They're able to do the subtraction. I'm just wondering if at some point might there be some tools developed within our organizations.
Okay, most photometry packages will give you an error based on Poisson errors plus things like read noise and stuff, the standard CCD equation calculation. But then you're also using comparison stars, maybe one or maybe an ensemble, and every one of those
has an error on it. So you should be incorporating the uncertainty in your comparison stars. And then if you happen to transform the data, you've got an error on your transformation coefficients.
That's right.
And you should be including those as well. So there's errors are really complex. There's a lot of sources of error in getting a photometry value that is realistically, has a realistic error estimated on it.
Well, I think at this point we should loop Bob Stevens in here because he's the accountant of us. And he can probably set you up with a credit and debit column for all of the positive things you may hope to achieve and the negative things. And a debit column is going to be huge, right? Defend yourself.
One other thing you can do if you're doing time series, and I quite often do this, is I kind of ignore the Poisson error or just put a note on my graph as to what it is. But then I plot K minus C, you know, and add a plotting constant to put it with the light curve. I find that that K minus C is, you know, you're measuring a K, you're measuring a C, the noise is there, and that's more representative of what your process is really capable of. And there are ways to get rid of the systematics, which I can talk about later.
Yeah. Well, the thing about K minus C is you take a standard star, or not a standard star, but just an assumed non-variable star. And you take your check star, which is something of a standard star, and you just, it should, the subtraction should be 0. And what we've seen in time series is it fluctuates. And the reason for that is the air is changing. And there's a couple of ways that air changes. If, like I was mentioning before, the lower in the atmosphere we live, the more we get it. The other aspect right now is something we brought up yesterday, and that is the fact that the sun is becoming active right now. And we're going to start seeing, you know, solar wind induced telerics that are going to start contributing. And we've seen the sky, particularly in red, change minute to minute under certain conditions. So these are all, like I said, the laundry list of, you know, in the accounting department. Asteroid, how do you asteroid guys deal with this thing? Because you do time series like the bandits.
Well, before I hand it to you, Eric Doe says online, never use one comp star in the age of deep catalogs. Use an ensemble of comp stars always, unless there's only one available.
I guess we got a mic. Yeah,
Okay.
we usually do ensemble, and it depends upon your target, how fast it's moving and everything. And obviously your ensembles are moving, you're moving across pixels, you're moving across background stars, you're stacking up errors on top of each other in addition to what we're normally used to in the variable star world. So at some point in time, you look at your results, you look at what's physically possible in an asteroid versus what's going on with the variable star. You keep track of the background stars that you can. I tend to look at every image as it's going by rather than just let it flow through a pipeline. I don't measure the images when that dim background star is creeping into the annulus. You do what you can, but you just know that you have a lot more sources of error than you would have looking at a variable star.
It's very true. And you have it in spades because your target is stretched and the stars are round, or vice versa. All the reference stars are stretched and your target is round.
Well, you try to avoid that, because if your target is stretched, meaning the asteroid has moved appreciably during the course of the exposure, you're introducing additional error in there. And at some point in time, you're increasing the noise faster than you're increasing the signal. So you try to avoid that. It's better to keep your exposure short in that circumstance and live with the noise.
Yeah, and that's something we talked about yesterday, particularly these CMOS cameras, is that we can reduce the exposure time to the point that we're keeping enough signal to meet our SNR requirements, a minimum amount of time so that we can keep the fluxes correctly, extract the fluxes image by image, and then co-add the numbers together. Don't try to stack the images and go after it in that fashion.
And to answer your question from earlier in the day and yesterday for a matter, when I interviewed many employees over the years and they start saying, what do you want 2 + 2 to equal? That's when you show them the door. The correct question that I always asked was, what's the difference between a debit and a credit? And if they start going, off and arm waving, you know that they don't understand the process. The true answer is the debit's in the right column and the credit's in the left column.
And the boss, he'll go, and he'll open up his drawer and put it closed. And the one guy came in at lunch one time and it opened it up and it said, debit, credit.
Well, I also accept that debit's by the window and credit's by the door.
There you go. There you go.
So, speaking as the other asteroid guy in the crowd, I always, what Bob said there, I always, and I would do this even if it's a static target, run a movie of the 70 or 80 or 200 images through the night. And I run it with a cadence of about 1/10 of a second. And then I'm recording along the way. Oh, it got cloudy or there's a gamma ray. There's something always happening on those images. So I always use an ensemble. And one of the features of MPO Canopus that I use every time is something that shows a plot of all 5 of the comp stars. And I've discovered new variable stars that way by seeing these periodic fluctuations. So you can see if one of them has a bad magnitude, or you can see if it's just bad. That and you want to do that every time.
Yeah, Tom's saying you plot each comp star against the ensemble of the other comp stars, and you can see some very interesting things over the course of the night.
Right. I'll talk in a minute about data informatics, but John?
Yeah, again, from Eric, he says, read his papers in 2020 and 2021 and use a pill-shaped aperture for moving targets.
Okay, one last thing on the asteroids, in addition to what my good colleagues have been saying, is we also cheat and we bin results of sequential ones. We put 3 observations in one bin to beat down the noise. We don't actually try and bin the images, but we will bin the results.
Yeah. Yeah, that's called a boxcar averaging technique, I believe. So informatics is your friend. When you're planning your observation, Gaia's been flying. Gaia goes down well below what we can see. And so you know where your 0 point is. Usually it's about 25th magnitude for a 1 meter telescope. I think that's the way it's calculated. But the result is you can get a database and you can say, is my target going near something that I haven't detected that may significantly, and then what I can do is I can cut my exposure time off, let it glide past that thing, pick up in my cadence and go again. David, no, Jerry.
Could you speak, or maybe the group could speak to color matching your comp and check stars to your target star?
Good question.
All in favor, say aye.
I would just comment one thing in anticipation of my talk later. And no, I'm not going to say everybody should read everything I've ever written. The doing this comp comparison business is an interesting challenge when you're doing a binary that has eclipses and one star, the red star is available, then the blue star is available, and you never know which mixture it really is. And so you might as well do a whole ensemble and make sure you got a mixture of reds and blues, and then you can sort it out maybe sometime later.
Yeah. Yeah. Okay. So I hope we kind of got into time domain observations, which is another form of photometry. I think Bob and Woody and some of the guys with the Red Dwarf group, you guys were hitting some interesting issues in there. Would you care to comment on any of that? You were doing both. They were doing simultaneous photometry and spectroscopy. So,
Well, you'll see some tomorrow.
okay, but just brief. Can you give me the elevator speech? Get on the elevator.
Well, read David's paper. I'm not sure what when you see a really dynamic target in photometry and spectroscopy, there are forms of activity that correlate nicely. You can see the photometry change and the spectroscopy change, and there are differences between them because the photometry is interrogating a different group of wavelengths than the spectroscopy maybe. Gary, you want to elaborate on that?
What I wanted to say to kind of answer Wayne's question is that we had instances where we had simultaneous spectroscopy and photometry And there were little blips in the photometry that particularly I would have called noise, but the fact that we had also a blip in the spectroscopy at the same time, just so that those little blips that we would have normally said are too small are actually real. So in spectroscopy.
And the thing to remember that they were doing is while they were doing simultaneous observations, they were using two OTAs, either widely separated at the same site or maybe even on the same mount. So that's two different cameras. So occasionally you're going to see a blip that shows up and it's probably an artifact of the camera. But if you catch it in two different systems, that's good concrete evidence that you're actually have some science. And that goes down to how do you know to get rid of an observation? David?
Another thing to comment on is typically your spectroscopic observation will be 10 times longer than your photometry, your individual photometric observations. So with photometry, you'll get a detailed shape of a flare star peak, for example. The spectroscopy will wash a lot of that out.
Exactly.
And you've got to bear that in mind when you're interpreting what you're seeing from the two different technologies.
Mm-hmm. Mm-hmm.
I have a question for John Hoot. You mentioned doing the averaging of 3 data points on your asteroid light curves. Do you take 1, 2, and 3, and then 4, 5, and 6, or 1, 2, 3, 2, 3, 4? So it's not a sliding boxcar. You're binning by threes. Got it. Thank you.
Okay. Yeah. And that's something we should probably look at maybe doing in a Zoom-like environment where we can have a more time to dwell on it rather than trying to do pretty broad blanketed type things. But I think my original question from a moment ago still stands. How do you know to throw a bad observation out? Gary?
The other idea is I've measured it once, that's it.
Yeah.
Speaking of ensemble photometry, picking your ensemble stars, this is precluding asteroid work. Do you pick stars brighter than, dimmer than, equal to? And do you perhaps want to weight the ensembles based on brightness to cut down noise?
And how do the different software packages do it?
I pick comp stars that are as bright as possible and still in the linear range of the sensor. And if my target is 2 magnitudes fainter than that, the sensor should be linear down to that. So I don't try to pick comp stars that are the same magnitude as my 15th magnitude asteroid. I'll pick 13th magnitude comp stars because you should have that linearity. You want to maximize the signal of your comps, your signal to noise of the comp stars.
And so one of the tricks that I do is I go up onto, used to go up onto pan stars at MAST, or what I would do now is go to Tonray's RevCat 2. And even though this is a completely different filter system, regime, the whole thing, they have a large number of observations of just about every star that you can find down to reasonable magnitudes. And what you do there is you say, and one of the things their databases report is the statistical variation of those guys. So you say, give me all stars that have, say, at least 20 observations for which the sigma is on the order of 0.05 magnitude. And that means that for all the times that pan stars looked at this thing, what was being a good little boy sitting on its stool, it was flat and constant. And those would be the ones that I would favor in putting together an ensemble. Then the other thing I like to do is to take the ensemble all the way down to the 0 point magnitude, where 1 photon is basically 1 photon per second. And then what you can do is you can go back, and for any field star that you have, you can assert what that magnitude would be. Now, it's a little on the inaccurate side because you know colors, a few other things to go with that. But what you wind up with is you find the guys that are well behaved, and anything that's outside of your acceptable tolerances, you mark those as being to be avoided, and that kind of tends to sigma clip, bring down the level for that ensemble line. And you can do that from field to field. You can also, if you're doing the same target over and over again, you can do it from night to night.
I comment on throwing out, quote, the bad data point. If you're God, you know which one is bad, but if you're not God, you have some idea, but you don't really know. And I personally have tended to follow the method of keep it all in, every single one, unless it's an obvious total mistake artifact.
Right.
I keep every single one in all the way through. It makes graphs look terrible. It makes the scatter look terrible in graphs. You'll see one this afternoon. But at least I always keep being reminded that there's a lot of stuff going on in there. And if I end up needing to give an accurate answer for one question, then you can at least start arguing throwing out this data point versus that. And this is true both in spectroscopy and in photometry. And in spectroscopy, your signal noise ratios are often much worse, at least point by point through the spectrum. And you better be really careful about trying to throw anything out, unless you only do what somebody referred to in my first year in physics. We were taught the basic rule that you only measure something once, because then you know the answer.
Right, right. Yeah, my rule of thumb is if it's a cosmic ray and if I can fix it, then I put it in and I mark it as an error bar or an exceptional piece of the observation. But if it's a really nasty thing, and you know that's where it came from, that it did not come from your science. That's about the only time you can have a legitimate excuse. John?
You finished it up. I was going to say, but you know what a cosmic ray looks like.
Yeah.
So you can say that.
Well, even systematically, you can know what a cosmic ray looks like. The way you find cosmic rays automatically is you say there's a general trend going up, say, the side of an airy disk, and you see something that's sticking way up here that's 1 pixel wide. Then you know, have a pretty good idea that that's an interloper. Okay.
Or probably an interloper.
Probably, yes. Yeah. There appears to be an interloper. Gary.
Yeah, what I've been doing recently, mostly this pertains to time series, is I'll get a light curve, and if either the target or the reference star or the check star shows, that it's out of population, I go look at that image and see if there's a cosmic ray or a hot pixel, or if the sky brightness has suddenly increased, or if the intensity of the target stars have decreased. And if I can find a reason like that, I delete it. Otherwise, I leave it in. So it's, you have to have a criteria. That's the criteria I've been using. And I probably have deleted some science, but I don't think very much.
Yeah, one of the things that we've seen, and I think I saw this a couple of times for you, Gary, and some of the stuff you put up on red dwarfs, was a cirrus cloud or something moseyed into the field. But what you'll find there is usually, if the stars are close enough together, they'll track. And you don't care that it dropped down. You just want to stay that they stayed the same.
Yeah.
It doesn't track perfectly. Yeah, there's a color component in there for
Well,
sure.
no, and one side of the field can be obstructed, but not the other side. So if you're
Yeah, as I said, if they're close enough together to begin with, and now we're in the if range, if maybe what's,
I had one other comment. The gentleman beside me, I'm not sure I know your name,
Tom,
who talked about looking at every image. That's a crucial thing to do. It's time consuming as heck if you've got 200 or 300 images, but that you got to do it. The other thing you can do, and many of us I'm sure do it, is deliberately start doing several sets of diagnostics. So graph the all night long version of 3 or 4 different things, look for any anomalies, and then track that. But it takes some self-discipline to do that, because you're always tired and busy, and it's the next morning, and to heck with it. So, but I think it's not so much throwing out a data point as understanding what you've got.
Well, bad data is just a good excuse to improve your systematics. David.
I think you have to convince yourself you've got an argument that will stand up in court before you throw a data point out.
Referees can be brutal.
Yeah. And the other thing that I suffer from is because I live near an airport, I get aircraft contrails coming through. the whole time, particularly at certain times of the night when all the planes take off, and that's a real pain.
You know, I had dinner with Arlo Landau at one time, and I was sitting next to him. I'd say, "So, what do you think about contrails?" Boy, did I put my nickel in.
And is your standing up in court, is that the Hurd and Adept trial, or which trial are you talking about?
You get to stand in a position roughly like I'm in now behind the dock. The truth is only in focus in a very narrow band. Okay, next question, Eric. Yeah, we probably can.
Changing topics a little bit, I have a hardware question. Are there any commercial cameras?
Hold it up a little bit closer. There you go.
Are there any commercial cameras that are configured or readily configurable for time
integration?
Time delay integration.
Oh, yes, I know what you're talking about. That's where you're shifting the pixels along.
That's right.
Well, quite a few of them do it, Arnie. I think, I don't know that the CCDs not so much because they don't have that ability built into them. Not CMOS,
Yeah, no.
CMOS, excuse me, I misspoke myself. The CMOS cameras not so much, but the CCDs will do that.
Yeah, and I think the SBIG cameras basically come with that capability. If you look at Maxim DL, it has one of the options is TDI.
I think the SBIG cameras will do TDI, but only for a small number of frames, only for a short period of time. Now, I'm thinking of something where you could run it continuously all night long.
Yeah, that
The Apogees would, but not under Maxim.
But you're right. The thing is that a CCD can do that because you're moving charge along a column.
Right.
And so it works fine. But with a CMOS camera, they don't have that kind of capability. So you don't gain anything by doing TDI with a CMOS camera.
So do you know a specific manufacturer or a specific camera that is configured for that?
Well, like I said, the closest you got is the SBIG driver. And you say it doesn't work for extended periods of time. So then I don't know.
Yeah.
Yeah. The CMOS, the readout times are so quick, and you can also region of interest them in some ways. So there's some games that you can play because TDI was okay. Back up a second. I know half of you guys in here probably don't understand what we're talking about. Time domain integration is where they would basically take an image of a star and they would allow the mount to mistrack a little bit, so they could be just shifting that target along, and it would be tracking it from time to time. And the good advantage of that is they were taking essentially decent integrations without having to have the readouts in between. And then they just clock it off the edge of the chip, take that result and send it out. And they're never having to stop and burn 15 or 20 seconds to empty the whole chip. John.
Yeah, what Eric's project has done historically with its time delay integration is to basically have a mount that does not track, or it tracks at an offset rate. And basically you just sit there and you clock across at sidereal rate. You just get this giant ribbon at a specific declination.
Mm-hmm.
Yeah, none of the off-the-shelf software is going to do that for you. The SBIG cameras and other CCDs, if you can get into the firmware to the readout electronics, to the clocks, all can do that magic trick. But as people have been saying with the fast readouts of the CMOS stuff and the modern stuff, you're probably better off if you have a tracking mount, is basically to track and get your integration, and then with overlap, snap to the next one, integrate and go. But if you're going to try and use the legacy equipment you've got, you're going to have to get in and write the readout routine.
And the great virtue to that is you have no money tied up in anything that isn't collecting photons. Exactly.
Yeah. Okay.
When we were on the EXO project, they used to do TDI, but they did it in declination. So the RA drive was on, and they put up a 85-degree strip. It was all the same RA, and by doing that, you can do the TDI at the rate you want to get the exposure level you want. But these were all custom drivers
Okay.
for Apogee cameras.
Well, we're getting, I think, a little close to time. Rachel, how are we doing? We're going to 2 o'clock? Okay. Well, I'm not getting ready to stop right now. We've had a major request, and that was for Arnie to reprise some information about observing Polaris on maybe a technique method by method. So Arnie, you want to come up and?
Oh, do I have to come up? It really doesn't account. The first place to look is that there's a paper by Nickel and Calderwood in the Journal for the AVSO, volume 49, number 2, about their observations of Betelgeuse during the big dip that they had. And that gives a pretty good explanation of how to observe during the daylight. So that's a good starting point. What we typically do when we're doing daylight observations is you just dither from one exposure to the next, and you can subtract the 2 exposures, and that gets rid of the sky background. And so that's the thing that varies. And once you do that, what happens is that for a star in the field, you will get a positive image and you'll get a negative image, but the sky gets subtracted out. 10, 15, 20 arc seconds, something like that, just enough to get you out of the seeing disk of the star that you're trying to follow. You don't want to move so far that you lose your comp star, which may be in the same field. So once you do that, you dither, you get rid of it, and as long as you haven't overexposed anything, which is the tricky part, then everything else just follows through after that. It's just like doing normal photometry. The advantage with Polaris is that it's not pointed towards the sun at all. It's not moving through the sky at all. And so it's about the easiest one of these daylight targets that you can find to do observing.
There's an idea I had after we walked away last night was something I plan to do. And that is to put a small refractor that looks at Polaris all the time. And it has a detector on it. And that becomes something like a seeing monitor for me. Because I'm looking at, how speckly is it, how much am I seeing is. But, you've just given me a project that I can do. You can run that thing all night long, okay?
Yeah, that idea isn't original. It's called a Polaris monitor.
I know.
Yeah, so that basically is like a Polaris monitor. The only difference is that you're actually using filters on here. And so the other thing you can do is add a neutral density filter until the sky background is decreased to the point where, it's reasonable. But you still, the dithering idea is the best way to get rid of the sky background that I can think of. So I've done it both ways, and it works. And I've done 10th magnitude stars in the daytime, and you can do it. You just have to watch for it.
Well, you mentioned this yesterday, and it's a trick. The dithering trick is well known in the infrared community because the sky is always bright. And so what you do is you just move back and forth, and the signal will always be on top of the sky. If you subtract the sky out, you've got the signal left. Did you have a question? Or are you stretching? Greg? Okay.
You can download the software for the Polaris monitor off the SBIG site.
Okay. Okay, so that kind of takes care of your contribution for Polaris. So whoever asked the question, does that meet your requirements? Okay. And so Bob also has, I believe, a slide that he would like to bring up. And that way we can, I think there's a couple of questions he wants to rip off that slide. Do you not have the slide?
Yeah, we loaded it. But this will probably end up being the last topic so that we can have a 10-minute break before we reconvene at 2. Okay, see how much you can blow that up. We had this long discussion yesterday about CMOS performance curves. Here is one for a camera I happen to own. And there was talk about a kink in the performance curve and I got to, let's see, the top graph is full well depth in electrons versus gain setting. And then the second one is gain in electrons per EDU versus the gain knob on the camera. Third one is dynamic range in stops versus gain. And finally, read noise in electrons RMS versus the gain setting. And there was talk about a kink in the curve that had something to do with the amplifier change. Could somebody point to where that is?
The answer is different camera, different chip. I emailed
Yeah.
Wayne and Arnie both the Sony short spec sheet for that. And they explain that for that particular chip, they actually have 4 tiny pixels that they bin together. And there is one way where they equally weight the gains and sum them. And then there's another one where they unequally weight the gains and sum them. And they pick a specific gain setting at which they start playing the game where they split them and with different exposures and co-add them in a funny way. And it's called their high dynamic range mode. And it solved the mystery for me as to what they were doing.
And the main point on that is that it is one camera. I've never seen that done on any other camera in the CMOS world. So, take it with a grain of salt. That's the 294.
Okay, there's something I'd like to point out on on Bob's chart here, and that is the two. Oh, my graph just got covered up. That's no noise. Okay, we'll just leave that right there for just a second. If you take the middle graph and the bottom graph is essentially a log plot of the top graph. That's all that difference is. It's a 20 times the log of something over something else. I can't remember what they are.
Okay, thank you. Question number 2 is full well in electrons is a function of gain. Is that right?
Yes.
Something about turning the gain up makes the well hold fewer electrons? Okay, now you're getting there.
All right, it is a gain setting. So ideally, I look for a camera where at the lowest gain setting, it will fill well and still be linear. All right, because what it is gain. How many ADUs do you generate on average for an electron? Oh, it's a gain setting. All right. So, my perfect camera if it has a 16-bit A to D, it's got a well that is not going to overflow with 65,536 electrons. And I have a 16-bit A to D, and I'm getting all my money's worth there. But if I double the gain, I get to 65,000 with a half full well. That's as simple as I can put it.
One of those is a dud.
Bob, here's your kink. So if you look at
Yes.
the last 2 charts, that's where the switch over happens. So you'll notice that the full well depth does continue to come down, but all of a sudden your dynamic range and it's the bottom one.
So one of
the read noise, yeah, you see that huge jump in read noise when they switch the amplifier.
there are several. There are several cameras like
This
that.
is the IMX 455, which is used in the QHY 600 and the ASI 6200.
Yeah, same basic pixels.
So the other thing to consider is instead of changing the gain on the amplifier to get that that disconnect, what happens if you take the well and cut the well in half? So the well is a capacitor. And if you have 2 capacitors with a FET between them, and you turn the FET off, you now have a smaller well, but your gain is such that you can't use the bigger well anyway because you don't have enough bits. And now you've got the equivalent of a higher gain system with no noise, with no added noise. So I don't know, but that's what it looks like to me they're doing.
That's a speckle trick, as I recall. You guys have discovered that with the speckle crowd. Okay.
Okay, thank you, guys. I appreciate the info.
Okay, so we have one other kind of outstanding question that doesn't exactly deal with too many things. And one of them is, well, I want to touch on one that came in. How do we get rid of telegraph noise in photometry? I'm going to table that one because that's probably a approaching infinite discussion. I think that we're still putting our heads together on dealing with some of that. That's going back to testing some images and seeing what we can get away with. But Eric brought up an interesting point about how do we go about getting collaboration? So we've talked a lot about all of these techniques. One of the things we desperately need to collaborate on is testing these cameras and testing these instruments. That's part of it. You're looking for some people to come work with you. Stephen Hill from this morning was looking for people there as well.
I think a really interesting thing would be, are there any kinds of databases of particularly overseas observers where we could expand the longitudinal distribution of collaborators in observing programs?
A good person to ask about that are our British contingent here, David Boyd and Tony Rada. David, you've been around. Tony, you have any ideas on that? Would you share some ideas with us?
Elaborate on that.
It's just, so basically the question is, if we have a bigger spread across a bigger longitude, you get things like you can fill in holes for photometry. You can watch stars longer. The short answer is yes. I mean, how do you want to set it up?
Is there a willingness in the BAA? Are they looking for us while we're looking for them?
They don't know you exist.
Okay.
You know, I mean, everybody's wrapped up in their own programs. There's very, very few people. There's only the ARIS people and CBA who do this right across the globe. So we need those kind of programs.
Absolutely, yes. But they self-organized in many ways. I think in some ways we're coming up in for example, the FLARE project that you guys were working on, you were looking at for FLARE frequencies as well as types, and having the UK anchor one side down and have California with Gary anchoring essentially the other side down. You know, if we'd have gotten Paul Lucas or somebody wrapped up in this, we'd have picked up Australia. So I actually think that's a great question. And I think a lot of our amateur groups tend to be a little bit regional, and somebody can take that on. ABSO's worldwide. I think maybe having something, opening up a discussion in these newsletters would be a good first step.
There's a lot you can do with that approach.
Yeah. Well, one of the things that we discovered, and this is an extension of COVID in some ways from a couple of years ago, is Bob and I and a few guys, we decided that we were going to open up and have these intermediate events. SAS was always designed to come here, and this is the party that we put on. We bring people together, they have their discussions, a form of collaboration, at least at the national level, occasionally the international level. And at the end of that time, we go away and that's it. This time what we did is we opened up some stuff. We started a group to build, starting with the low spec spectrograph. That's going to conclude 3 years worth of a project tomorrow morning. The Red Dwarf group came along. We took advantage of some of the free internet services like Groups.io, for example, to open up a mailing list that brings people together. A project that Greg and I have been interested in working on is this amateur astronomical telegram service. In other words, throw out all those 75th magnitude Swift detections and only bring us stuff that say starts at 15 or 16 and gets brighter. It's the basic, the bright sky belongs to us, and the high cadence long observation periods belong to us as well. David?